In this lesson, we're going to talk about continuity and the intermediate value theorem. We're going to start off with this definition. It says a function f is continuous at a value a if, and we have these three conditions. The first one says that f of a has to be defined, or we can note a is in the domain of f. The second condition says the limit as x approaches a of f of x exists, meaning the limit as x approaches a from the left of the function is equal to the limit as x approaches a from the right. And then the third condition says the limit as x approaches a of f of x has to equal f of a, and that means there will be no break in the graph. So for example, if you took a pencil and you traced the graph, your pencil wouldn't lift off the paper. A little notation, if any of these conditions are not satisfied, then we would say f is discontinuous at a, or we would say f has a discontinuity at a. And that leads us into the different types of discontinuities. We have removable, jump, and infinite. For removable, we have this function right here. It's a rational function. I'm going to go ahead and factor the numerator down below. So the numerator factors to x minus 2, x plus 1, and now you'll see that you have common factors on top and bottom that are going to cancel. So f of x becomes the function x plus 1. Because these factors canceled, this graph will have a hole at x equals 2. So you'll see from this graph you have a hole right here at x equals 2, and this is called a removable discontinuity. And again from this graph you can see that the function is not defined at 2. So I wrote that out, f of 2 is not defined, and because the function is not defined at this given x value, we would say that the function is discontinuous at x equals 2. And again, that's because one of the conditions for continuity is not satisfied. The next discontinuity that we're going to look at is a jump discontinuity. So to demonstrate that, we're going to look at this function right here. Because of the absolute value in the numerator, we want to look at the limit approaching 0 from the left and the right. So if you recall, the absolute value of x is equal to positive x when x is greater than 0, and it's equal to negative x when x is less than 0. And again, if you think of the graph as a V, to the right of 0, the graph has a positive slope, and to the left of 0, the graph has a negative slope. So because first I want to take the limit as x approaches 0 from the left, we replace the absolute value of x with negative x. The x's cancel, and you get the limit as x approaches 0 from the left of negative 1, which just equals negative 1. We're going to do the same thing approaching 0 from the right. Approaching 0 from the right, you get, instead of the absolute value of x, you get a positive x. So now these x's cancel, and you end up getting the limit as x approaches 0 from the right of 1, which just equals 1. So I wrote this out. Since the limit as x approaches 0 from the left of f does not equal the limit as x approaches 0 from the right of f, we can conclude that the limit as x approaches 0 of f of x does not exist. And so therefore we can conclude that f is discontinuous at x equals 0 because one of the conditions is not satisfied. So we just demonstrated this algebraically. It's a jump discontinuity, but I'm going to show the graph so we can see it visually. So since the limit as x approaches 0 from the left equaled negative 1, from the left you have a constant height of negative 1 for this graph. And then the limit as x approaches 0 from the right became positive 1, so you have a constant height of positive 1 coming from the right, approaching 0. And you can see from this diagram we have a jump discontinuity. This last graph 1 over x is an example of an infinite discontinuity. This graph has a vertical asymptote right here, therefore it has an infinite discontinuity. Because of the infinite discontinuity, I want to show the limit as x approaches 0 from the right versus the left. So if you look at this graph, as you approach 0 from the left, the height of the graph is going to negative infinity. Next, we want to look at the limit as x approaches 0 from the right of f of x. From the right, you can see the height is going to positive infinity. We have that the limit as x approaches 0 from the left of f is not equal to the limit as x approaches 0 from the right of f. Therefore, the limit as x approaches just 0 of f of x does not exist. Therefore, we can conclude that f is discontinuous at x equals 0. And again, we call this an example of an infinite discontinuity. So to recap, we have a removable discontinuity, where if you look at the graph, you have a hole. You have a jump discontinuity, where you can see the graph kind of jumps. And for an infinite discontinuity, the function will go to infinity. This example says determine whether the function is continuous at the given value. So we have a rational function and we have x equals 3. To figure out if a function is continuous at a designated value, you're looking at the three conditions for the definition of continuity. If all three are satisfied, then the function is continuous at that value. If one of these is not satisfied, then the function is discontinuous at this value. So we're going to start with the first one. We're going to check, is f of 3 defined? So right away you can see that if we plug in 3 for x in the denominator, you'll get 0 on the bottom, which will make this not defined. And because the first condition of the definition of continuity is not satisfied, we say that f is not continuous at x equals 3. For this problem, we have g equals, and we have a piecewise function. So I want to look at this numerator and see how it factors. So you can see that you have x minus 2 on top and bottom, so those factors will cancel and it leaves a whole at x equals 2. For a piecewise, you're checking to see if it's continuous at these values over here. And if we want to specifically check if g is defined at 2, we're going to take 2 and plug it in. Because it says right here that x doesn't equal 2, that means we're using this condition right here. It says g, if x is 2, will equal 1. So we can conclude that g of 2 is defined. Next, we want to see if the limit exists. So to apply that to this problem, we have the limit as x approaches 2 of g of x. And remember, to evaluate a limit, you want to check the function as it gets close to this value from the left and the right, but we're not necessarily worried about what the function does exactly at 2. So that means we're going to use this part of the piecewise up here. Our work on the right showed that this expression equals x plus 1, so that's what we're going to plug in. And to evaluate this, we're going to use the direct substitution property, and we're going to plug in 2 for x. So you can see that this limit exists. Third condition is saying that parts 1 and 2 are equal to each other. So for part 1, we got a value of 1, but for part 2, we got a value of 3, so therefore r's are not equaling each other, so let's go ahead and state that. So I just wrote that out. We have the limit as x approaches 2 of g of x equals 3, which doesn't equal g of 2. Therefore, g is not continuous at 2. This theorem says if f and g are continuous at a value a, and if c is a constant, then the following functions are also continuous at a. So that just means if you take two functions that are both continuous at a value, if you add them together, the sum will also be continuous. Same thing with the difference. If you multiply one of them by a constant c, if you multiply them together, or if you take their quotient, all of these will still be continuous at that value. Then we have this following theorem. It says any polynomial is continuous everywhere. So that would be from negative infinity to positive infinity. We also have that any rational function is continuous wherever it is defined. That means it's continuous on its domain. And last, we have the following types of functions are continuous at every number in their domain. So you have exponential, logarithmic, polynomials, rational, root, and trig functions. This example says to show that f of x, which is equal to sine over square root of x, is continuous on its domain. So I just made a note that sine is a trig function, therefore it's continuous for all real numbers. Next, I have that the square root of x is a root function, therefore it's continuous from closed bracket 0 to infinity. And then finally, we have the entire function sine over the square root of x is continuous on the open interval from 0 to infinity. So I made sure not to include 0 here because square root of x is in the denominator and you can't include 0. This example says given the function, we have f of x equals this piecewise function, and the designated value is going to be a equals -1. Part A says explain why the function is discontinuous at -1. So this one isn't asking whether or not it's continuous at a value. It's already telling us that it's discontinuous at -1, and we want to show why. So first I want to just check, is the function defined at -1? Right here the interval is x greater or equal to -1. The key is that or equal to -1. So we're going to say in order to find f of -1, we're going to plug in -1 right here into this bottom part of the piecewise. So f is defined at -1. Part 2, we need to see if the limit exists. So we're checking as x approaches -1 from the left of the function. Since we have as x approaches -1 from the left, we're going to use the top part of this piecewise because it says that x is less than -1. This is a rational function, so at this point we can take -1 and plug it in, and you get -1. Now we're going to do the same thing from the right of -1. Because we're approaching -1 from the right, we look right here and it says x is greater or equal to -1. So that means we're going to use the bottom part of the piecewise. To evaluate this limit, we're going to pull the square root to the outside and take the limit of the inside function. And at this point, you can plug in -1 and you get -1 plus 1 is 0, or the square root of 0, which is 0. So I wrote it out. Since the left-hand limit doesn't equal the right-hand limit, the limit as x approaches -1 of f of x does not exist. And because the limit does not exist, the second condition of the definition of continuity is not satisfied, so we can conclude that f is discontinuous at a equals -1. Part B wants us to sketch the graph of f, so we're going to sketch this piecewise function. So remember the graph of 1 over x looks like this. So when this says f of x equals 1 over x for all values less than -1, I started at -1 is a height of -1. put an open dot because it says x less than -1, and the graph is going to continue to the left and approach a height of 0. Next, we have the square root of x plus 1, so that's a square root graph that's been shifted left 1. And here I have my square root graph shifted left 1. And remember, square root graphs, if the front value is 1 and there's no number in front of x, then it follows the pattern over 1 up 1, go back to that first dot, over 4 up 2. Here's our piecewise function, and you can see that it has a discontinuity at -1, and you would call this a jump discontinuity. Here we have a theorem. It says if f is continuous at b and we have the limit as x goes to a of g equals b, we have this theorem. The limit as x goes to a of f of g of x. So if you have a composition of functions, you can pull the outer function to the outside and take the limit of the inner function right here. So we're going to apply this theorem in this next problem. We have the limit of sine of x plus sine. So to evaluate it, we have a composition of functions. We have sine of x plus sine. So we can pull this sine, because it's the outer function, to the outside, and then we can take the limit of the inside function. So I have it set up. Now at this point, we want to find the limit as x goes to pi. Using the limit laws, I rewrote this as the limit as x goes to pi of x plus the limit as x goes to pi of sine of x. According to the direct substitution property, we can plug pi right in. To evaluate this, we can look at the graph. For the sine graph, as you approach pi from the left and the right, you can see that from both sides you're approaching a height of 0. So we get sine of pi plus 0, or just sine of pi. So our final answer is 0. We have a theorem: if g is continuous at a and f is continuous at g of a, then the composite function f of g, or we write it as f of g of x, equals, and again, as a composition, is also continuous at a. Finally, we have the intermediate value theorem. Suppose that f is continuous on the closed interval from a to b, and let capital N be any number between f of a and f of b, where f of a doesn't equal f of b. If that's the case, then there exists a number c in an open interval such that f of c is equal to that capital N value. So here's our diagram. We have an interval from a to b. We have that f of a and f of b are different heights, so you want your endpoints to be different heights. And then finally, we have n is a y value in between f of a and b. If all these conditions are satisfied, then the conclusion says there exists a number c in between a and b, so it can't be on an endpoint, such that f of c is equal to that n value. This example says use the intermediate value theorem to show that f of x, which equals this function, has a 0 between 1 and 3. So in order to use the intermediate value theorem to show that this function has a 0 between 1 and 3, we want to show that the hypotheses of the intermediate value theorem hold true. So I wrote out, since f is a polynomial, it is continuous for all real numbers. Next, we're going to take these values 1 and 3, we're going to plug them into the function. When you plug in 1, you get positive 3. So I just wrote greater than 0 to show that I know that this value is positive. Next, we're plugging in 3, and you get -1. So since one of our n values is a positive and one is a negative, our next statement is going to point that out. So the negative value was f of 3. So since we know that one n value is negative and one n value is positive, we know that there is now a number c in the open interval from 1 to 3. So this weird little e right here is saying c is an element of the set of numbers from 1 to 3. So it's basically just saying that c is a number in between 1 and 3. And then we write such that f of c equals 0 by the intermediate value theorem. Our last statement is just writing out what we're trying to show. Therefore, f, which equals x squared minus 6x plus 8, has a 0 between 1 and 3. The last example says if f of 1 is -5, f of 4 is 5, does there have to be a value x between 1 and 4 such that f of x equals 0? So I drew a diagram. We have f of 1 is -5, f of 4 is 5. This is not drawn to scale. Because we have one negative and one positive value on this graph, it says does there have to be a value in between 1 and 4 such that the function will cross the x-axis? The key to this is the answer is no, because it never states that the function is continuous. So there could be a discontinuity in between 1 and 4, and therefore this doesn't have to hold true. So this is just showing the importance of the hypotheses of the intermediate value theorem in order for the statement to hold true. So let's go ahead and write that out. So to answer the question, no, if the function is not continuous on that closed interval, then there doesn't have to be an x value where the graph hits the x-axis. All right, guys, thanks for watching.